from that density. So the higher the density, the greater the risk if you have a failure. So at the very top is NMC, and this is what Tesla used in their first 18650 cells. All right, that's the most energy dense technology. But it also burns hot and can produce its own oxygen because, in large part, due to the cobalt. When it's acting, it's evolving oxygen. As we go down in energy density down to LFP, the safety increases. But let me say one thing that's really important. All of these can go into thermal runaway if raised up to enough temperature. Okay, so LFP is not immune from thermal runaway. It takes a higher temperature. Okay, there's some other actually issues with the LFP that I'll touch on in a little bit, but in general, it is considered a safer chemistry. The main thing is not having the cobalt. The cobalt from a environmental and human what's the term I'm looking for? Human rights. Thank you. Yeah, you're using children as your slaves. Not a good thing. Okay. Mike talked a lot about cylindrical cells. He showed pouch cells. The other one is prismatic. It's just a form factor. All right. So cylindrical is obviously a cylindrical. Pouch can be many different shapes, so it's very flexible in designs. And prismatic would be anything with a rigid shell case that has corners on it, essentially. Okay. Not one of these is necessarily any safer than the other. I will say though, there is a safety benefit to cylindrical, and that's because it's typically small. If you do have a failure, you're not going to get as much energy out. And because it's round, they're not touching other batteries on all sides. You have a little more air around them, okay? So just from that one perspective, it does offer some benefits. The larger cells, when you have a single cell failure, you're going to have a lot of gases coming out. And that's the one area of concern I have as this industry is growing. We're moving to larger and larger format cells to the point to where a single cell failure could put you in explosion risk. Voltage. Let's talk a little bit about voltage. On the residential side, batteries are typically between 48 volts and about 600 volts. All right. If you happen to approach a scene and you see open bus bars, in other words, there's nothing, no plexiglass or no metal over those, that's less than 50 volts because that's the threshold from OSHA for touch safe. Okay. If anyone's ever been in a telecom basement with just, rooms and rooms full of lead acid and NiCad and iron batteries, those are all at 48 volts. You can touch those. Okay. On the commercial side, it goes typically from around 480 volts up to 1500 volts. Okay. And what's key, I keep pointing the pointer at a television screen and it just doesn't work. They will exist after utilities are shut down. Even on a residential, you shut off all of the disconnects that you see, batteries are still energized. I think you all understand that now, okay? But let me just show you what it really means. Mike talked about state of charge. And for lithium-ion batteries, 100% state of charge is around 4 volts. Actually, it should be 4.2. And 0% state of charge is, 2.8 to 3 volts. It's 0 volts. That's really key. When we talk about a 1500 volt energy storage system at 0% state of charge can still have over 800 volts on that system. Okay. So this is another little check mark in the box of why defensive might be a good idea, to utilize that fuel, to de-energize it and not have that stranded energy issue when you can go defensive, obviously. So what are the concerns of the fire service? In the order of responses that fire service is going through, this is it right here. The micromobility devices, the scooters, the e-bikes, mountain bikes, they are failing at a far greater number just because there's so many more out there. And there will continue to be more. I have an electric mountain bike. I charge it outside. But here's an interesting point. You see in a lot of news clippings about these incidents, how it's in the fire, going in and out. use the charger that came with the equipment. Use the manufacturer's supply charger. Well, I bought a bike from a company. It's always the battery. Test, test, test. Okay. Take the ends. Okay. So the bike that I bought, the charger that came with it was garbage. It charged to 100% state charge at a set current all the time. I had a more advanced charger because I had built a mountain electric bike before, work in this field. The advanced from 100%. So I want to charge my usually percent. I very rarely will use that one. Sorry for the folks online here. And then I also charge it at a lower current. Okay, so there's an example how just because a charger comes with a device doesn't necessarily mean that it's very quality. Okay. The next one are EV fires. And we're not seeing as many EV fires in structures, but that's obviously the biggest concern. When it comes to your strategy, it's all about protecting exposures, life, and property. So if it's in the structure, you are going offensive, obviously. All right. I don't know if anyone remembers seeing this one here. This is in Canada. This is a vehicle that had a bad day. And thankfully, it removed the garage door. Those are always fun trying to remove on the fire scene. So this one was already removed for them. But it also removed the roof. So that's not good. And then lastly, it's the stationary storage. All right. Thankfully, there's not a lot of those fires that are happening. And when the stationary storage is outdoors, that's a good thing because all there is to protect is other equipment. All right. All right. So earlier, Mike again talked about why they fail. These top two, electrical abuse and thermal abuse, are the majority of why cells fail. I would say maybe internal faults go up on the top there too. It's difficult to really say why it failed because this is what it looks like. All right. I have so much respect for, ATF and their ability with their CAT scans and to really identify the failures. But it's really difficult in that pile of molten aluminum and copper and plastic. But the bottom line is once you have a failure, you have thermal runaway. In thermal runaway, you have flammable gases. And if they don't ignite, you have an explosion risk. And then after all of that, you have a stranded energy issue. Yeah, we don't need to go over that. Just one last thing here on this one. The fires can continue in low oxygen environments, all right? It should be kind of obvious at this point that there is no holy grail when it comes to fire suppressant agents. There really isn't. And you'll see marketing out there from different clean agent manufacturers and aerosol manufacturers. And they're even putting them in energy storage systems and kind of selling them as fire suppression for the battery. They're fire suppression for visible flame. All right. All of those agents work great on visible flame, but not on deep-seated battery fires. And that's the issue. You'll even see demonstrations on YouTube where they'll have a couple of cells or a module sitting on a bench and put it in thermal runaway and apply their agent. Well, that's an exposed module or exposed group of cells. Let's put it into a module that's covered with steel inside a rack with 20 modules on top of it and see how it works. So it's very difficult to admit that we don't really have an effective agent, but we have to be honest about that. And so it's a very exothermic reaction, incredibly hot. You have a lot of different chemical reactions happening at that same time. And we talk a lot about significant cooling with water. I will actually present the suggestion perhaps that, water might not really be as effective as we think it is. I like to say water is actually a double-edged sword because not only is it great at cooling, It's pretty darn conductive too. And the largest battery in the world, does anyone know where the largest battery in the world is? No? It's 30 minutes from my house, Moss Landing Power Plant. Okay. And I've been out there many times, and they had a fire that had nothing to do with the batteries going to thermal runaway. They had a ventilation system with a bearing burnout, pump a bunch of smoke inside the building. This first phase of their battery, it was built inside an old turbine building. All right, so they have 5,000 battery racks inside a huge building. The smoke detection system detected the smoke, has no idea where the smoke's coming from, pressurizes the sprinkler system that's designed for these battery racks. You know, I had a sprinkler inside every module. And then due to poor craftsmanship and commissioning, water sprayed everywhere and started a lot of fires. So there's challenges with water. And we've used a lot of waters on some fires. All right, so, okay, now this is one video he didn't show, but many of you have seen this. Has been around for a long time. I like this one because it definitely shows you the speed of the gas evolution. Okay, so here we've got, but just by show of hands, how many people have seen this video? Okay, yeah, almost half. Okay, scooter on charge, dad, daughter, and the puppy. Okay, we got a pop, no audio. So the gases are going to come out very quickly. You know, these scooters, the batteries on these are maybe 800 watt hours. Okay, they had about 3 seconds to get out of that room. And the evolution of gas, I'm really interested in this one because, you know, these 18650 cells this pack was likely made up of, you know, you get a decent amount of gas out of one, but that was a significant amount. So that was a lot of cells failing at once, which is an interesting phenomenon. Okay, here are the gases that are evolved from kind of a mix of the different chemistries. Not every chemistry evolves all of these. These are gases that have been measured in lithium ion. The majority is the carbon monoxide and hydrogen, and it's generally between, you know, 20 to 50% of each, depending on the chemistry. Okay, and let's see, in Arizona, they picked up a lot of hydrogen cyanide. And that comes from wiring insulation and plastics. The hydrogen fluoride that we heard about earlier, that's a very reactive gas. It's really hard to measure. But now when you apply water, you get hydrofluoric acid. So again, that's another, you know, question. Is it making it more hazardous by putting a lot of water on these? Okay. Any questions so far, any of this? Okay. So on the residential side, there have been a number of incidents. I'm just capturing a couple here. We've had one in San Jose. This is actually in my district for my station where I retired out of, but it happened after I left. Another area in California. This manufacturer did a voluntary recall of a number of their systems due to some defects that they had found during their manufacturing process. This was a top tier manufacturer. Okay. So, you know, it's very difficult to design a system to operate safely. It's very difficult. Germany has had a number of incidents. This one right here, they took the battery out on a dolly and it caught fire as they were moving it out. That's very challenging. It's very challenging to leave something inside a house. You want an overhaul, you want to get it all outside, but it's challenging if you don't know if it's going to ignite again. South Korea has had probably 30 to 40 failures of large stationary energy storage systems. And it was a victim of a significant amount of building happening with very limited regulations. Okay. And so there's a couple of the main commonalities between all of these fires. None of the systems in Korea were listed to UL 9540, which is the listing for stationary energy storage systems. And I'll talk more about that in a little bit. Now, was that the reason they weren't safe? You know, a lot of these issues right here are addressed in 9540. So I said a minute ago, it's very difficult to design a safe system. There's a lot of factors that are going into that complexity. And it's not just chemistry based. There's manufacturers out there that were touting their LFP as being, it won't go into thermal runaway, and that's just simply not true. You can have a fire starting just from a single cell. You could have a defect, and you can't design against that. You just have to ensure that it doesn't get worse than that one cell. But how the whole system is integrated, from the cells to the battery management system to the communication, it's all really critical. Earlier we were talking a little bit about the battery management system. We're going to take a little break in 2 minutes. It's puffing? Okay. Battery management system does not know when a cell is on fire from a hot cell. It just doesn't. It's just dumb circuitry. It's looking at voltage, current, and temperature in a few locations, right? It's not measuring the temperature of every cell. It can, depending on the size of the cell. But where you're using 18650s, you're not going to have thousands of thermocouples coming out, okay? So that's one thing to understand. You guys just yell when that thing pops. I'll stop talking. Okay, now to that point of LFP, this is an energy storage system that's using LFP that bursts into flames on its way from the factory to the customer. Wasn't connected, nothing's on. How does that happen? Well, what do you think was going on? What was one of those failure modes possibly? Internal mechanical? Vibration? Yeah. When you get up into the higher voltage systems, 1500 volts, that they call creepage and clearance between conductors is really critical. Or do they do vibration tests of any of their components? They did here. It didn't pass. And how long do you think this shut this highway down? All right, a long time. Okay, I'm going to go ahead and take a break here, and we'll switch it over on this screen here.
All right, so they, that wasn't quite as dramatic as it was last night. But, so goes the experiments. I think we're just going to see that. We don't know the state of charge. That box was just how we received it. So they're going to extinguish it here any second. And once they do that, they'll come in. But for now, if you want to go ahead and we'll restart your presentation and rock on.
Do you say you knew what state charge is, or they don't? We did not.
Yeah, there's a completely
That would have been interesting to know, to take a voltage reading off it and see what the state of charge was. My guess is very low. Yeah. Which, that's good to see.
Oh, but the problem is dealing with multiple battery packs,
Yep.
multiple types of batteries, chemistries. A battery pack is, one cell could be fully charged, one could be dead. And that's why it's in the bin.
Right.
So,
Was it FSR? No. UL's Fire Protection Research Foundation did a whole commodity burn test with battery packs and cardboard, and it wasn't as dramatic as people expected. So, there's a lot of common combustibles in these toolboxes. All right, let's see. Where is my presentation at here? That's not what we want. Is that working? It was? All right, hold on. It's because it's a Mac.
I did just watch the cell and what was going on in there. Yeah, so like I said, that
What are we
was,
seeing out there right now?
That was up on the top part, this swap splits.
Yeah, I got to look at that while I move my mouse here.
I'll talk about this.
Yeah, you
just
do
a
your
little bit,
thing.
and then we'll break, and then maybe you continue.
Carry that up.
Here you go, Mike.
How's it going, guys? So we set off that first one like we were talking about, where we had the cartridge heater inside with some lithium batteries. As you can see, there was early on 4 distinct kind of explosion events. Those were the 18650s in the immediate vicinity of the cartridge heater. This box, like that you see up here that you can look at during the break, is rated with some fire resistance associated with that blanket within it to prevent flame and fire propagation out of it once the failure occurs. But that looks like a burned up box in a pile to me. We killed the cartridge heater as soon as the first batteries popped. So at that point, it was just the batteries propagating and then the flaming impingement upon the cardboard, allowing it to continue to burn. So this is basically the scenario of a energized battery that was disposed of in transit with one of these boxes, going into thermal runaway and the subsequent fire that you see. Now remember, when these are transported, it's several of them on a pallet or several of them in a truck. So what we're going to do now is they're going to extinguish it, and then they're going to take it up. There they go. They're starting to extinguish it, and then they're going to quench it in a bucket with water, and then they're going to do some water sampling associated with the post-fire contents of the packaging itself. The next one is going to be similar, like I said, and we'll hope to bring it on the big screen. That's going to be fire impingement, and it's a little bit higher mix of lithium versus NiCad and stuff. So you may get a couple more pops and everything going off. And then we'll take a look at how fast your not the fire progression compares to this one where it internally failed. Because obviously when we're internally failed, we had that blanket which contributes to potentially containing the event. From the outside, we're getting the cardboard going right off the bat, right? And now we have this blanket that's supposed to prevent some of the propagation to the inside. So we'll see how that affects it. And the next round. Want to take a break and then come back, or go ahead? They did, yes. So both CST and the other guys did some sampling where they collected the gases that were in the container itself as a result of the fire and while it was burning. And now they're going to conduct their analysis and stuff. And we'll see what we get off of that or where it goes from there. But yes, we're doing that on every evolution that we do here. All right. Want to take 5 minutes? Want to give us a good time for them to break, or you want to continue?
Yeah, that's fine. Yeah.
All right, yeah. If you guys want to take 5 minutes, and then Matt will continue, and then we'll move on.
Yeah, give me a high five. Okay, we're going to get going again. So this next one here, I'm sure everybody has seen these videos. These were all over YouTube. Paris, like many cities around the world, is electrifying their transportation. So they get a bunch of electric buses. But when I saw this video, the fire behavior of this video really got my attention because I've seen a lot of lithium-ion batteries put into thermal runaway, and I had never seen a behavior like this. So let me play this for you. Actually, I have to go out of this to YouTube, which should have it ready to go. Are we seeing it? Yep. Okay. So we don't have audio, unfortunately, but it doesn't matter because it's just some music. Okay, so watch this. Look at those sparks. It's Mount Vesuvius, right? Yeah, batteries on the top is not typically on the bottom. That might have been hybrid, but either way, it is definitely a lithium-ion battery. What was it? Molten, well, it's molten everything right now. And then it just kind of ends the way they all end, which, you know, smoke and flames. Okay, so when I saw that, you know, I was really curious what it was, and so I did a little research. So who made those cells? And I found out the company, all right? It's actually called Blue Solutions. I'm not knocking the company, but when I go to the website, this is what I'm knocking. All right, let's be very honest about the technologies. Now, I haven't checked the website lately, but this is fairly recently, and those fires were months ago. So anyways, now these batteries, they call them LMP, lithium metal polymer. Okay, this is a solid state battery. Now, has anyone ever heard of solid state before? All right, it's been kind of touted as the safe lithium-ion battery. All right, now solid-state batteries span a range of designs and a range of electrolyte amounts, from no liquid electrolyte to some liquid electrolyte. And the cathode in this case is a lithium metal, no lithium ion salts, and that's the sparking that we saw in there, was that lithium metal reacting. So one of the challenges with solid state batteries is to get a true non-electrolyte or, you know, solid electrolyte. It's very expensive and very difficult to make that separator. All right. Now, when I say separator, we've got the anode and the cathode, and the separator is it keeps, you know, the two families happy. You know, you want the ions passing through that separator, but you do not want those two sides to touch. And there is a failure condition where the normal cycling of the battery, now let's talk about just a standard electrolyte-based lithium ion, where the lithium can start to deposit in little crystalline structures. It looks like a little Christmas tree, and it's called a dendrite. And it's a conductive path, and that dendrite can actually pierce through the separator. And so that is one form of an internal defect that can cause thermal runaway. When we're heating cells to thermal runaway, what's actually happening is, we saw in that CT image, the electrolyte starts to vaporize, all right, and starts building up pressure, and then it pops the vent, and you get that electrolyte venting coming out. Well, if the heating continues, that plastic separator will melt. The first stage of it melting is it will not allow ions to pass through it anymore. The sign is that the voltage drops. If you're monitoring, the BMS is looking at those cells, it sees the voltage go from, 4 volts to 0. Okay. The next stage is that plastic separator of melting and direct short circuit. So thermal runaway actually kind of has 2 stages. You have venting, and then you have full thermal runaway. All right. Okay. Any questions about that right there? It's still on the website. All right. Well, and I think there's definitely an interest in solid state. And Sandia Labs actually they put out a paper recently that talks about these different solid state risks of different types. And it's a really good paper. Okay, let's touch on codes and standards. Hey, who's the person doing codes and standards? Tomorrow, I think? Not here? Right, the guy right there? All right. Sorry, buddy. Okay, so here's the main codes and standards that address energy storage. I made this graphic up. I didn't do it myself, but somebody at the lab did, because I wanted to be able to show a good graphic for where do these different standards fall into the place. So when we look at the overall installation, we've got NFPA 70, that's the National Electrical Code. Then we have 855, the International Fire Code, a UL standard, and the IEEE C2 is the National Electrical Code for utilities. They follow it. It's called the National Electric Safety Code. They have their own, would be covered by that. When you're connecting it to the grid, there's some IEEE standards that for interconnection that have to be followed. And now when we open the system up and we look at a battery rack, that's the cells in the battery. 1642 is what an individual cell would be certified to. A battery to 1973, and a battery could be one or more cells with a BMS. So that's 1973. And then 9548 is the fire testing of this, okay? Here's an important part. To be listed to 9540, you have to start with a 1973 listed battery and pair it with a 1741 listed inverter. And that right there is one of the barriers to a second life battery getting off the ground, because these are batteries coming from vehicles that are not listed to any of these. So right from the get-go, that battery doesn't have that listing to ever get it. Plus, you're never going to fire test it because it's a destructive test. Oh, I'm sorry. Second life is when you take the first life would be in your car, all right? And once it's reached 80% of its capacity, manufacturers say that it shouldn't be used for vehicles anymore. And then they either recycle them right now, but people want to basically make stationary energy storage out of them. And we're doing some research at our lab to, take old bus batteries and turn them into a stationary storage for the bus facilities. We'll see whether or not there's enough revenue there for someone to make that work. Okay. So here's the two main fire code documents. We got the International Fire Code and 855. 2023 is out right now. The printed copy you can order in December, but right now you can view it online. The design of the system, the hazard mitigation analysis, how you commission it, how close they can be to get all of these different things, decommissioning, emergency response training, the whole section in there. The IFC has very similar language in the 2021, and the 2024 just got completed, but when will it be out? Does anybody, we have an ICC person here? 2023, I guess I have it on there. So Washington is going through it to adopt the 2021. Yeah, but the 2024 edition just got kind of all voted and completed. And anyways, this line down here is a really key one. I'm sorry for putting it at the bottom of the slide there. Everybody can do that whole thing. In both 855 and the 2024 IFC, there is a requirement, or there's a language in there for requiring an HMA, hazard mitigation analysis, on unlisted existing systems. So it gives the AHJ an ability to go and say, hey, that system that was installed 5 years ago, let's see what the risks are and come up with a report. That's going to be problematic for some of these older systems, because what they're going to find is the explosion risk wasn't addressed, and doing that retrofit is going to be really hard. All right, everyone's seen this. It's a patchwork quilt across the whole U.S. Wyoming's the only state that's on the 2021 right now, the whole one. California has brought forth the 2021 language on energy storage into it. Yes, sir. Oregon's on it? Okay. All right. Yeah, I just actually went to the ICC website to see if it was an update. All right, good for you, Oregon. Okay, so the HMA, there's 3 criteria that trigger it. All right, some technology that's not on that table in 855, multiple different technologies in a room with the potential for adverse reactions, or when you want to go over the maximum allowed quantity, 600 kilowatt hours. All right, so then you do an HMA, and it's looking at all of the different possible failures, single point failures. What happens when you have thermal runaway in a battery array? the energy management system fails, a ventilation system fails. So it's looking at what all the what ifs are if this happens. Okay. So the whole 3-foot size and separation, when this was first introduced in the codes, that's what we said. We said you can't be larger than 50 kilowatt hours or closer than 3 feet apart without doing a fire test to tell us that it's safer. And the industry said, where'd you pull that 3 feet out of? We said, exactly. Tell us a better number because we don't have the data yet. All right. So it was absolutely an arbitrary number, but you have to start somewhere. So what's happening now with that 9540A test is it's becoming more and more required on every system because they're all bigger than 50 kilowatts. They're all sandwiched next to each other. And my hope is that 9540A kind of goes away and all the requirements for it, the test, just get lumped right into the 9540 listing. And that every test, every battery has to go through that. All right, manufacturers probably hate me for saying that because it's really expensive, but we've learned a lot about battery design by doing that. Okay, so now let's jump into the explosion control. So there's 3 ways of meeting explosion control in 855. And, you know, I talk a lot about 855. I know I'm in an IFC area, but this really is it's kind of, and we heard it earlier, it's really going to become the key document that is referenced for energy storage. So the first one is NFPA 68, deflagration venting, all right, pressure relief panels. Okay. The next one is deflagration prevention to NFPA 69. So some kind of exhaust system that's going to keep the gases below 25% of the lower flammability limit. And then the third option is some performance-based design, an engineered cabinet that will not allow no pressure waves, no projectiles to be ejected, and it's based on the large-scale fire test. So it has to be evaluated during that test, all right? Now, let me share my personal opinions about these. I don't think this should be allowed by itself. You know, each one of these, you could do any of these currently. I don't think this is a good idea because it only works when there is an explosion. You could be at 100% of the UFL and no explosion occur, and who's going to go open that door? All right? Where's the probie? All right? So it is, it's not, I have no problem with people wanting to do an exhaust system and that. Okay, that's fine, active and passive. The truth is when you really calculate how much square footage you need to release the pressure, when you're calculating on hydrogen, there's not enough room on most of these enclosures to do the panels. All right. Okay, so what I'm going to show you is something that we looked at as an option. Oh, I'm sorry. No, I'll get to that in a minute. Okay, yeah. Are we ready? Okay. Oh, yeah, that's probably the big screen. No worries, no worries. Flexible. All right. Don't look at the fire, right? Okay. So we've heard a lot about 9540. It's for the whole system. It's not, I was on a webinar earlier, and it was for a bunch of installers. And, you know, one of them was saying, so I've always built battery system with just a bunch of other listed components. You mean I can't do that anymore? Yeah, pretty much you can't. So it's kind of rough realization that they can't take that battery, the lead acid battery they've been using for 25 years, an inverter. Now it's got to go to UL or some other lab, and they have to pay thousands and thousands of dollars. I get that, but we're dealing with this came about because of lithium ion. So lead acid has an easier path, but it looks at how it's constructed. It goes through mechanical environmental tests, vibration, EMF, communications. We want to know functional safety. We really want to know, do those components really work with each other? They work by themselves, that BMS, but does it really work with this charge controller? And what kind of thermal management are you using? Are you using liquid cooled, air cooled? It looks at that. And then there are requirements for the fire testing under 9540A. So again, this is not a listing or certification. It's not a pass-fail test. And you'll see manufacturers that say, 9540A approved or certified to 9540A, and that's a misuse of what it is. And that's why I want to see it go away. It is a standardized test, and it's used to give us data. It tells us how much it propagates, what kind of gases come out of it. And because explosion control is required, you need to do this fire test to know what kind of gases you're designing for. So it's really critical. Now it starts at the cell level. If at the cell level, it can't go into thermal runaway or produce flammable gases, you're done. Okay. Can anyone think of a battery that might meet that won't go in thermal runaway and doesn't produce any flammable gases? Any thoughts? So what's that? Yeah. AGM, so lead acid. Actually, lead acid can go, it can experience it. Valve regulated lead acid, okay? Because you're getting hydrogen whenever you charge a lead acid battery. So if you're not controlling that, but it's a little bit different of a reaction, but that's close. You're still generating hydrogen when you're charging. Yeah, or if it doesn't builds up. What was that? Gel. No, all the lead acid, anything that produces hydrogen when it charges, and so I was going to say flow batteries could potentially be that, but there's still some question about hydrogen production using some electrolytes in a flow battery. And just for those of you who don't know, a flow battery does everyone know what a fuel cell is? Where you've got, again, a membrane, and then you've got, in this case, you've got electrolyte on one side and a different electrolyte on the other side. And with pumps, you're pumping it across a membrane. And when you get those two dissimilar electrolytes, you get a little bit of a charge across that membrane. The thing about the safety with them is they're not a flammable electrolyte. They're typically an acid-based. And then when you shut those pumps off, there is no stranded energy. So, but there is still a little bit of concern around some production of either chlorine or hydrogen, but that's potentially one that could meet that. Obviously, mechanical batteries aren't going to do that. But okay, so now we've determined, all right, it does go into thermal runaway, produce flammable gas. We now do a module level test. And this is where we want to see, what does it take to drive propagation? Okay, so you have to heat cells until you get a fire in an unheated cell. You might need to heat many 18650s to drive one that's unheated into propagation, into thermal runaway. Or a prismatic cell or a pouch cell, you might only need to heat one and it's off to the races. So what we're seeing now is modules that are designed with really unique materials and phase change materials, aerogels that really limit propagation. And the unit level test is what we're seeing right here, whole bunch of modules. And the goal in that one is to see, can you get fire outside of that unit? And if you do, then you go to the installation level test, which requires a fire suppression system. Because the goal is not to have propagation to the next unit. Even though I talked to you, there's not really good fire suppression. If you're having flames come out, those flames could be suppressed by an agent, right? But it's limited in its effectiveness. Anything exciting happening there? They put water on it? Okay. Okay, so, so I just went through it. Here is a prismatic cell, and what we're seeing here is thermocouples on it, the different locations, and then they put it into this inert chamber. And what they're doing in that test is they're seeing what temperature does it vent, what temperature does it go into thermal runaway, and then what gases come out of it. How fast do they come out? What's the total volume of the gas? And then what's the lower flammability limit of that mixture of gases? Okay. So then here's that module level test. They take that same cell and put it in a module, and they want to see what happens when they heat that. And they do it underneath the calorimeter hood. And it's at this stage here that measuring the gases is not very good. You look at some of these fire reports, 9540A reports the module, and it'll say no hydrogen detected. When we know at the cell level test, it might produce 100 liters of gas, 4% hydrogen. So it becomes a little harder to measure the gas, but they are doing this at this stage as well. And we also want to know, what deflagration hazards there are. Here's the unit level test. So the initiating unit, we want to know what's the temperature on this unit, what's the temperature on the walls, and that will help inform, can you have it right next to it, or does it need to be further away? And you can't be more than 97 degrees above ambient, Celsius, above ambient. Okay. So I just reviewed a test report by manufacturer, and this one has to have its batteries in it. These don't have to have batteries, but they have to have thermocouples. And the temperature on this one was above the thermal runaway temperature. So it would have driven. So that's not a good test. All right. Pretty much just went over this here. Okay, this is kind of a busy slide, but this is really important. When we talk about explosion control, we have two main codes. We have the International Fire Code, which is adopted by most states. Then when you have A55, which is only adopted by about 5 states, but most federal facilities follow A55. Both of these require listing to 9540, right? So we're telling everybody it's got to be listed 9540 and 9540A. So that's part of the product standard. The explosion control, there was a TIA, a tentative interim amendment, which is a change in the code, issued stating that the explosion control requirement applied to cabinets too. A lot of manufacturers, when they first started making these big energy storage systems, were putting shipping containers, Connex boxes with a man door and an aisle and batteries on either side. Well, manufacturers started making them in cabinets, and a cabinet means there's no man door. You can't go inside it. Everything's accessible from exterior doors. Okay, and because the word cabinet wasn't included in a lot of sections of the code, they thought it doesn't apply to us. We got a cabinet. So we went back and said, nope, cabinet applies for explosion control. And that right there, the problem with this is a manufacturer could get it listed to 9540, but now the fire code or A55 says you need explosion control, and it might require a complete redesign of the system. This should be in here, should be in the product listing, and it will be hopefully next year. But I am seeing a lot of projects where, like a utility, for example, they'll put out an RFP for someone to bid on it. They'll bid it. They're going to put in this kind of system, and they get it listed, and then the fire marshal gets involved and says, where's your explosion control? And the system's already built and already tested. And it can take months and hundreds of thousands of dollars to redesign that. So it's a big gap. Here's a little more on a residential fire. So in this Google image right here, here's a PV system over a car park. And over here on the Charlie side of the house, or Delta side, there's a staircase that goes down below this raised deck. Here's the staircase. When you get to the bottom of the staircase, turn around. Here is the battery and an inverter on the wall. The PV system was installed in 2017. The ESS was added in 2019. All right, it's all installed to code. And this was a LG Resu ESS engine 19, my old crew. Homeowner noticed some buzzing about 1:30 in the afternoon, and the lights went off. Went outside, and this thing was on fire, rolling under the roof of the upper deck there. So the battery was used for what's called load shifting. It was running during the expensive times of electricity. I don't know if you guys have that out here, but in California, energy is more expensive from like 10 to 7, 10 a.m. 7 p.m. So they'll pull everything off of the battery during that time and then charge it at night. So once a day it was cycled. But at the time, there was no requirement for this to be listed to 9540, nor for fire testing. And this is exactly why they all need to be fire tested, because when you look at this, here's the metal racks that the battery is hanging on. This T111 wooden siding burned right through it. Flames burned right through the 1/4-inch aluminum back on this battery, right in there. All right. So we need to understand what happens during thermal runaway to make sure that either the installation instructions say don't put on combustible surfaces, or do something to keep this from happening. And there was a recall on this. Okay, so we've seen and heard about explosion risks. It's already resulted in fatalities. There was 3 fatalities in Beijing and this fire right here. A couple of very serious injuries in Arizona. And since there's very limited fire suppression options, you know, a defensive firefighting approach is becoming more and more discussed and even, you know, utilized. However, the explosion risk has to be addressed. Now, there was I don't know how many of you have heard about this one, but this was a utility installation in the UK. And back in 2020, in September, there was an explosion around midnight. This system is owned by an operator in Denmark, and they were using it for frequency regulation. In other words, they were just injecting power very quickly to keep the frequency of the voltage right at the desired hertz. Here's the system that went unhappy at midnight. Now, there was no notification to the fire department, to anybody prior to the explosion. All right. So it was probably a good thing because there was debris that was thrown up to 60 feet away. So it's probably good that nobody was there. But this was a system where there was no deflagration venting. These are not deflagration vents. They're the HVAC units that got thrown off. But the fire department just protected the exposures for the most part. They directed a hose line inside this opening. So you can see some of the images here. Very limited ability to get their lines anywhere. However, they flowed water for 59 hours. Right? So in California, that's a natural disaster right there. It was many years ago when we had to even stop our Sunday hose drills of flowing all of our nozzles and doing all that just because of the public outcry over it. So a couple of things that they learned: there was no training provided to the fire department at the time it was commissioned. There was no alarm communication that something had gone bad. There was an explosion. London Fire Brigade has really good hazmat crews. I don't know if any of you have ever had any interaction with them, but they got their stuff together. So they did really good airborne and water monitoring for the duration of the event. And the interesting thing, they actually found a little bit low pH, and they think that it might have been from the buffering of all the lime rocks around the site. So I thought it was interesting. You know, there is one thing to say about a lot of water being used when it comes to contamination, right? Secret of pollution is dilution. Okay, I didn't say that. So they came out with a set of recommendations: have an on-site pre-plan and a risk assessment, HMA, retrofit vents and pressure relief valves to the containers. All right, what did I say? What was my opinion about pressure relief valves? Matt's not a big fan of them. Let's use deflagration prevention. Let's not let the gases build up, right? If they want to do that on the top as well, that's fine. Have in-rack suppression, as the external system may not penetrate the racks. Okay, now we've seen that. Remember that big battery I told you near my house, Moss Landing? That has in-rack water suppression. Now, as long as there's not a bunch of leaks in the system, it might work. But even if you have thermal runaway in one rack and the sprinkler opens up and now you have 5 gallons a minute flowing out that module down onto all the other modules, and where is it? So water is a tough one. Markings externally to the containers to notify crews where a lance or stinger. That's an interesting one. I don't know that I would really want people throwing a piercing nozzle into there, but obviously they're saying, show us where there's no batteries to do it. We probably should be using more piercing nozzles here in the US, but not necessary for this application. Okay, external audible and visual warning, absolutely, all right. They talked to denote if the detection system's activated or a suppression system been deployed. There was a Novec 1230 system on here that did not deploy. And I don't remember what the reason was. I think it was not activated. Like someone had done maintenance and didn't activate it again. Blast walls across each entrance and between units to reduce the fire blast risk. Again, deflagration prevention systems missing. Okay, so here's one in Creo. You saw that picture. So let me show you what we at PNNL thought might be an option for system designs. And as an example, this is a 1.4 megawatt hour battery at a utility over in Arlington, Washington, Snowpud. The background on this, we call it IntelliVent, was we've seen explosions that have almost killed firefighters in Arizona, did kill firefighters in Beijing. And the lack of exhaust ventilation was noted as the key leading gap. And other systems will have failures in the future. It's going to happen. And as people are moving to listing the entire system, it's going to become more of a cabinet, more of a widget. This system here showed what can happen when you don't have it. And in a system like this, where you have a lot of free air volume, because there's that whole walkway down the middle, think now if you have a cabinet where there's just inches between the walls and the batteries, a lot less free air volume. How quickly would those fans need to operate, even quicker? So it's going to be even more challenging to have an exhaust system in a cabinet. Hey, Derek, are you going to talk about this? Am I stealing any thunder? Are you presenting? Could I do this one and I do the water one and then the 3 takeaways? Okay. I should have a QR code because this report is outstanding. What UL did, they do a lot of 9540 tests for customers. It's all under NDA. They can't share the results. And they were learning so much about what makes a system that performs well. And so what they did is they said, let's make a generic system, do a generic set of tests to teach people what this test is, what it isn't, what it looks like. And they put it all into this report that was published a year and a half ago. What we're looking at in here is there's 3 demonstration tests. This is the installation level test. And what we're looking at is a rack that there's these modules that they made that are stacked with 18650 cells. It's not an operating energy storage system, okay? And they forced thermal runaway in one of the modules. And this one is to test a clean agent. So at 55 seconds, enough smoke is produced to trigger the clean agent discharge at 58 seconds. Well, clean agent has a limited soak time, all right? About 10 minutes, typically it's design point. So at about 26 minutes, it's stratified and where thermal runaway continues. It ignites, 28 minutes, and they have a partial volume deflagration in this test chamber at 44 minutes. And these are half PSI vents on all sides, all right? So they have a lot of square footage on there. You would not have that on a typical cabinet. Continues thermal runaway. At 2 hours and 9 seconds, or 2 hours and 9 minutes, they stop the test and open the door, flash over, and they have to direct a hose line in there to terminate it, all right? So that's with a clean agent. With water, they actually had to wait for fire to generate to build up enough heat to trigger the sprinkler system. So that took about 8 minutes. Okay? Now we can see in this image right here at the very top, sprinklers, discharge is doing a good job keeping the walls cool, keeping the other units cool, but the thermal runaway is continuing in that target or that initiating unit. And at about 30 minutes, the smoke is coming out from propagation. So propagation is continuing. It's not having an effect after 20 minutes of water flow. At 42 minutes, there's a deflagration. Water's turned off at about an hour and 13 minutes and continued propagation after that, okay? So the bottom line is that the deflagration vents operated, here's even flames coming out of them, in each of the tests, all right? They had the compartments filled between 40 to 60% of gases at elevated temperatures. And let me say one thing. The thermal runaway temperature of a cell very often reaches the autoignition temperature of hydrogen. So you could have a thermal runaway with no flames, but just the temperature of those gases coming out could ignite the hydrogen that's coming out. And lastly, the gas accumulation was not prevented by anything. So that's the data that informs my comments about we don't have a suppression agent that's really effective yet. There's a lot of interesting things people are trying. Okay, so the cabinets. Why is the industry moving to cabinets? More modular designs. It's safer to install because the batteries are very often preloaded in it at the factory. And they can get that widget listed. All right, so all of them are kind of the same. You're just building your plant off of hundreds of these. But the challenge is, again, a lot less air volume inside there to exhaust. So we said, okay, if these cabinets have doors, why can't we use the doors to exhaust? So this is a generic enclosure that's having some kind of failure inside. And the detectors that would already be installed inside it, whether it be gas or smoke or heat, they're monitored by the system. That's a requirement of 9540. And the system that we call IntelliVent would take that signal from the fire alarm panel and utilizing UL listed access control devices, open the doors at a very early stage. So this iteration of this concept would utilize mag locks, say at the top and bottom, and these are like 600-pound mag locks. You cannot open them. And then a passive opener, gas spring, spring hinge. And you could utilize a keypad for manual opening. You can also have a remote manual button so that somebody just showed up, having received an alarm from a safe location, they could push a button and the doors all open. So it gives you that situational awareness of what's really happening inside there instead of having to send the probie over to open the door. All right. Now, we started out with a patent application on this. And I shared, well, that puts me in a really awkward spot because I think this is a great idea. And I want everyone to use this. And because PNNL gives a little bit of a few coins to their inventors, it puts me in a conflict spot of recommending it. So we abandoned the patent search, not just because I said that, but they just felt that we didn't want to be a barrier to any manufacturer using any way of their doors. All right, so nothing in it for me if people use it. So SnowPud, this battery, when they first designed this system, they reached out to us and said, what is the gold standard of safety for an energy storage system? What's available to use? We said, well, there's some new off-gas sensors out there that are just sensing for the electrolyte at that first stage of venting. There's VESDA, very early smoke detection. It's an aspirating smoke detector. There is exhaust fans. There's deluge sprinkler and clean agent. So they put all of that in this cabinet. Then when IntelliVent got introduced, they said, we're interested in that. And so this was kind of the first pilot project of it. And so this is a series of videos from inside. We put a smoke bomb, fire alarm test bomb inside there. And then you see the doors opening very slowly, smoke's coming out. Because there's doors on both sides, it evacuates that space very quickly. They're still testing the dampening on the opener, so that's why it's inconsistent. But it doesn't have to open fast. Just that it has to be forceful enough to ensure it opens. And once they did this, and then the fire department came back through, they said, because this has a dry pipe deluge system, that comes over to an FDC probably about 50 feet away. And their previous SOP was going to be hook up and look up and just watch it and just flood it. Now they said, we're probably not even going to use that system. All right, the door's going to be open. You've said it's okay to let it burn. We're going to let it burn, consume the fuel, not create a water issue because they were on top of an aquifer. So it's changed their operations. Any questions? Yeah. So will the gases cause environmental impact? Every fire has toxic gases, right? And what's one of the worst ones on a regular basis? Car fire. Absolute worst. But it's over in about an hour, right? So that's the big difference with an energy storage fires. It typically go for 4 or 6 hours. Another reason to consider allowing it to burn, because applying water could make it last even longer. I'll get back to your question, but it was a good one. There was an incident in Chandler, Arizona a few months ago, a utility-owned building that had 10 megawatts, 40 megawatt hours of storage. One had a fire, set off the overhead sprinkler system. There was no exhaust system designed into it, and there was a roll-up door, but it was a manual roll-up, and then a man door. And because they had no ability to get situational awareness on what's happening inside, the water stayed on, right? Anybody remember how long the water stayed on that site, or hear how much water was used? 10 days, 3 million gallons of water used, all right? All the batteries burned. How many of the batteries burned because of the water shorting them out? You know? So to your question, that's what I'm hoping that organizations like you do. And where's Mike? No, the smoke plume analysis is important because it feeds into the ERG distances. But yeah, that's exactly what's happening this week. I'm not going to even take a guess at that right now. Too many factors in that. Okay, so here's a small battery that we are retrofitting. That was another design criteria for us with IntelliVent, was we wanted to address the existing systems out there that have nothing. And so here's a small system. This is a 200 kilowatt hour battery, just 2 racks that we're using for building controls modeling. We do a lot of studies on the grid and how the grid functions. And so we use this battery to send signals and receive power. And so because this only has doors on the front, are we going to be creating gas pockets in there to where it's not really going to evacuate? Yes, sir. Oh, hey, really good point. Thank you. Yeah. Okay. Let me see how many more slides I got. I'm actually almost done. I'm just gonna finish. All right, I've only got about 5 more slides. I'm going to finish. Uh-oh. Okay, we're good. Okay, so to answer our question whether or not it would work with doors on the front side, we did a CFD model. And we used the data from the 9548 tests, how much evolves out of it. And what we see is at about 8 seconds, we have to trigger the doors. All right. And at the top of the plume, you're up at 25% of the LFL, but nowhere else. So the doors opening just on the front keeps the entire cabinet well below the LFL. So it's an effective way for us to provide deflagration prevention on our own battery. All right. And so the average cabinet percentage was below 4%. The code requires you have to stay below 25% of the lower flammability limit. We were well below that. Okay. So we expect to see a lot more systems consider this. We've seen RFPs of projects in the hundreds of megawatts by utilities saying they want automatic doors on their system. Now, what that will do, though, is if you do have a fire, now you've got a fire visible to the next cabinet. So the manufacturers need to know what that heat flux is and need to design their insulation and their distancing consistent with that data. So UL will get a lot more testing of these systems, but it's going to change the test because the current test does not require ignition of the gases. And that's a big gap in a lot of people's mind. So safety, this is always the issue, you know, how safe can you afford to make it when we're trying to make it affordable and reachable? I would love a battery at my house. I've got PV. I don't have an electric car yet, but I'm almost an all electric house. Switched off of propane to put heat pumps in for air conditioning and heating. And I would love a battery, but they're still too expensive. And I'd like something, I'm waiting for a little bit more development in this space. But the residential battery space is the one that I'm personally most concerned about. Because if I'm cheap, most other people are going to want an even cheaper battery. And what's going to get cut out when you reduce the margin of profit down? Safety, quality, right? And so because these batteries are currently allowed indoors, in basements and utility closets, we're going to see issues. Yeah. Ultracapacitors still have a significant energy release capacity. They go into thermal runaway massively. Yeah, yeah, yeah.
Have you looked at all of the graphene aluminum, or is that just marketing hype at this point?
So I would say that the technologies that might offer more promise has to do with some of the zinc technologies, lithium and sulfur. Let's see. That's the other scientists at my lab, material scientists, they have all these different materials that they're cycling through and figuring out which one's got good cycle time and good capacity. It's years and years from them developing it to having a product you can buy. So we're going to have lithium ion for at least another, I'd say, absolutely 5 years. Absolutely, if not more. Yeah. All right. Well, that's all I got. Thank you very much. If you have any questions, I'll be playing all week. All right. Thanks.
All right, we've got one last experiment that they're doing. Todd, do you know exactly how they're propagating this one? Okay.
I think we're getting really good data on water collection and the toxicity of the smoke. That's probably why they're doing another one. I think this is going to be flame infringement. They've got it up on a metal box, and so they should get the plants more under it and zero matter.
All right, good deal. If you guys want to take a break, there's probably 5 minutes before they actually ignite it and then a couple minutes before it goes. So at your will.
I don't want to melt the cord. That's good.
Yeah. All right, folks, we're going to get started here again. And I'm told I have to close this out at 4 o'clock. So, yeah, sharp. So we're going to do, I'm David Byers. I manage the statewide response section for the Department of Ecology. And I'm here with a couple other folks from Ecology. Sean Thompson, he is our spill responder, a lead responder from the Spokane office. So he's your local person. I am from Olympia. We've got one of our after-hour responders. I'll say a little bit more about that, that we have a program in ecology, and that is Martin Quinn. Martin's here. Martin, his day job is solid waste management with the Department of Ecology. And then Courtney Sherrod. Courtney's a responder, and she is hiding. She's hiding right now. So just a brief overview of the Department of Ecology, our spill response section, what we do. And then Sean is going to discuss how we got wrapped up into this event. I think Sean and some other folks saw a lot of potential in this event, and he got amped up, really charged forward. Come on, those are battery puns. Somebody please. Got potential, charge, amp. Okay, all right. Sorry. So we are in the spills program in the Department of Ecology. We're one of 10 environmental programs, things like air quality, nuclear waste management, solid waste, water quality, water resources. Bunch of programs, right? We do spills. We focus on spill response. 3 sections in our program. We have a commercial vessel, big boat, ocean-going size inspection program, and we also look at oil storage and production facilities, things like pipelines, refineries, and now we have crude by rail, right? Coming right through downtown Spokane. We've had 2 crude oil train derailments and fires that have affected Washington, one in Mosier, Oregon, across the river, one in the little town of Custer, just north of Bellingham in Washington State. Ecology got involved in both of those. So our prevention inspection does that sort of work, trying to prevent spills when they happen. We're doing this kind of cool thing, maritime risk modeling. So we're creating a maritime risk model of Puget Sound to look at the probability and consequences of what happens if 2 of these big ocean-going vessels bump into each other. We have a preparedness section working with the oil industry in Washington. Again, that's things like crude oil pipelines, refined product pipelines. We've got 5 refineries in Washington State, 5 crude oil refineries in Washington, plus a couple of smaller biodiesel production facilities. Big facilities that manage lots of oil and create lots of risk. They work with the industry to make sure that they're prepared for spills. There's a Yellowstone pipeline. It's predominantly a diesel pipeline that comes in from Montana, goes all the way to Moses Lake, passes through Spokane. We actually drill in this room. We have big worst case drills every 3 years. We test the industry, the oil industry. First, they have to produce a contingency plan. We test it. We look for weakness during our drills and exercises so we can improve the plan and be better next time we actually go through that drill cycle. We also worked on the maintaining the Northwest Area Contingency Plan. That is our multi-agency partnership with our federal response agencies, state, and even locals can participate, as well as tribes. We have a number of tribes that are active participants and responders in the state of Washington for hazmat. Let's see, and then the best, most fun section is the response section. That's the section we work for. We're responsible for oil and hazardous materials spills with the focus on impacts to water. The agency does impacts to the ground or soil too, and we get involved in that, but really we're out the door going on things that will impact surface waters or even groundwaters in the state. We are, in state law, responsible for the cleanup and waste and chemical precursors with every drug lab in the state of Washington. I want to thank the legislature for that. That has been keeping us busy lately. And also occasionally pulls in the 10th CST to work with us on things like fentanyl pill presses to manage the chemicals and narcotics associated with those sorts of hazards. We also have, some of you have talked to me about this when I've been here today. You appreciate the grant program that we have at the Department of Ecology. Chris is smiling. We give away about $3 million a biennium worth of equipment. By the way, that grant program is opening up again, I think, towards the very beginning of the year. So we'll have another, if funded by the legislature, of course, got to throw that caveat on there. We'll have another $3.5 million to give out for equipment and training. We have a restoration program where, as a result of spills, if you're the spiller, not only might you get a penalty from the Department of Ecology with our enforcement authority, but you're going to reimburse the citizens of the state for the damages that you occurred to our publicly owned natural resources. We take that money, we call them damages, we take that money and we reinvest in restoration work to rebuild those publicly owned resources that were injured as a part of the spill. And that's a restoration program. And then we also do investigations and enforcement, issue penalties. I've got a slide on our enforcement authorities that I'll show you here in a minute. We've got about 30 responders. So the yellow ones are full-time responders. Those are folks at Ecology. That's their day job. This is where they're parked around the state. And then we also have after-hour responders because we can't do it with just our full-time staff. So folks like Martin, who work other day jobs with the Department of Ecology, they bring in other expertises and skills and connections to other programs in the agency, like air quality and water quality, toxics cleanup. And we're better because of them. And they supplement our after hours and weekend 24/7 spill response capability. So we do have responders on 24/7 in 4 of our regional offices around the state. And we have the ability to tap into extra expertise if we need beyond the staff that we have on call. Some special services besides spill response and cleanup that we provide. We do a lot of disaster support. When disasters happen, there's an example of some of the things that we've just simply staffed the incident management team with. It may not be in our authority. It may not be our direct mission related, but we're going to help out other sister agencies if they need our assistance. We do have area arrays. We have multi-arrays to do community air monitoring. We've got particulate monitor that fractions the particulates by particulate size. I think the brand we have is Dustrax. We're working one right now at a fertilizer warehouse fire in Moses Lake, Grant County. Yep. We do have, we've got the FLIR and Raman spectroscopy. We do hazard categorization with field chemistry tests to test unknowns, predominantly for disposal, but also just to identify what it is. We have oiled wildlife response capability. We've scrubbed everything from ducks to heron to snakes, turtles, and let's see what else. Oiled wildlife falls within our responsibility too. We do have partners at the State Department of Fish and Wildlife that help us with that. One other cool trick that we have is we have authority to compel spillers to clean it up. And so if you've got a reluctant responsible party, a spiller that just looks at it and goes, don't worry about it. Well, we worry about it, and we actually have authority to issue an administrative order or direct them to clean it up. And if they choose not to, that can increase their penalty, or certainly we have funding to clean it up from the Department of Ecology, not in every circumstance, but in some based upon the restrictions on our funding streams. We can clean it up and send them the bill through cost recovery. So that's nice to have that authority given to us by our state legislature. When we do that, we recover costs, and we are a team that actually puts on the boots and suits. SCBAs, all of our folks are hazmat specialists. They're SCBA capable. We pick up a shovel from time to time, and if it's too much for us to haul in our trucks, then we'll bring in contractors and pay contractors to help us with the cleanup. So our enforcement tools. This is a list of tools we can use to compel spillers to clean up or clean it up and cost recover ourselves. We do have penalty authority from the legislature, and it tells us the legislature directs the Department of Ecology to issue a penalty to spillers who spill oil or hazardous substances into waters of the state. It doesn't say Ecology can think about it. It doesn't say Ecology might want to. It says Ecology shall issue a penalty. So we do have a couple of folks who are just dedicated to pushing enforcement actions out the door as a deterrent for folks to maybe prevent spills. We consider factors such as their willingness to cooperate, whether or not they took actions themselves to clean up the spill, or whether we had to step in and pay a contractor to do it. All of those things are factored into the penalty maximum. How much does a spill cost you if you're a spiller? The legislature set a cap on us of $10,000 per day charge for oil or hazardous materials into the water. Unless our investigation determines it's negligence, reckless, or intentional, and then that cap goes as high as $500,000 a day, not a discharge, but that oil or hazardous materials remain in the environment. So if you're a spill and it takes you 3 weeks to clean it up, then you know that, and it was negligent, reckless, or intentional, that your penalty can get big, very big, very fast. And of course, this third piece is this natural resource damage assessment piece, where we have 2 staff that work on determining what the injury was, what's the value of the injury to publicly owned resources. So what's a publicly owned resource? It's fish, it's water quality, it's public access to beaches, it's recreational shellfish harvesting, it's all of that stuff that we do out in the public that has value to us. If your oil gets in the water and damages that or interferes with public recreational or beach access, whatever, then you have to compensate us as citizens of the state, and we will work to rebuild those resources. And then finally, to close out, just some cool pictures of the kind of stuff that we get involved in. Of course, 5 refineries in Washington state, occasional gasoline tank barge that breaks free crossing the Columbia River. Woo, this is going fast. It's out of control. Custer crude oil fire north of Bellingham. Oops, wrong way, sorry. That's Custer again from the air. This was the Mosier crude oil derailment, which derailed. Somebody on an overpass snapped this photo about 2 minutes before it ignited and turned into this. A lot of meth labs, especially in the day. Fewer and fewer, but we still get them from time to time. The occasional chemical suicide that happens that we respond to and remove the waste after you all treat the patient. Occasional propane truck rollover, marina fires. This resulted in, this was in Gig Harbor, resulted in, of course, covered marina. You never have one boat burning in a covered marina, right? Usually any marina fire, I grew up in a fire department that had a marina. You always had 3 boats on fire. So fire where it started, then the fiberglass boats on either side burn up too by the time you get it out. Covered marinas, you're just going to lose the whole pier all at once. It's like preheating each boat on down the line, and it just cooks it. This resulted in about 7,000 gallons of fuel recovered after all the boats sank. Another good story. So our grant program, Gig Harbor, this was in Gig Harbor. The Marine Patrol used grant boom from our grant program, strung boom around this fire when it was early, before the boat sank, captured 100% of the oily debris and fuel that bubbled up, and it made our job so much easier following up to clean that up off the water surface after that event happened. Our contractors that we pulled in said you saved about $1.5 million in cleanup by giving Gig Harbor a few hundred feet of oil containment boom. We put out, this was back in 2007, we put out 99 equipment caches like this all over the state, and they've just used the heck out of them. The entire cost of that program was $1.5 million to put all those equipment caches out, and one fire paid for the grant program. Oh, yeah, gasoline tankers, occasionally, they run into things or they get into collisions and burn. This was no exception. This was on I-90 near Issaquah. Not only resulted in gasoline contamination going, but also, not these guys, this is East Side Fire Rescue. They were not using bad foam, but they couldn't get this out, and it was blocking traffic on I-90. And so we called in a foam tender from King County Airport from Boeing Field and burped this fire out with just like 15,000 gallons of foam all at once. That was PFAS foam. And that may explain why the Sammamish water supply is now, they've lost some wells as a result of that with PFAS contamination. And I know y'all are thinking about that, right? Ecology does have a grant program to replace fluorinated fire foams at fire departments around the state. So be looking for that. Ooh, too much. The occasional derelict vessel. This was a World War II Liberty ship that had 35,000 gallons of bunker fuel still in the keel. Somebody bought the ship, thought they'd make money off of scrapping it, wasn't really a marine architect, broke its back, started releasing bunker fuel, which was in the keel, and then we moved in, and this was the result. At about $25 million later, we disassembled the ship in the river and removed the fuel.
Where was that?
Near Camas, Columbia River. On the Washington side. If this were on the Oregon side, it would have been their problems. Darn it. And drugs. So the flavor of the day, of course, is sorry about the slide flipping. We're on autoplay or something. Marijuana is the flavor of the day. We'll do about 100 illegal grow operations. Why do we care about illegal grow operations? Well, of course, the drugs are, they're a bad thing, but it's legal in Washington, right? A lot of associated crime with this. Cartels are running these, tax evasion, human trafficking, and lots of toxic stuff that we bump into, such as the pest control devices. Those are aluminum phosphide cylinders, super toxic. Aluminum phosphide reacts with humidity to form phosphine gas, and a very toxic gas. Remote grows, the team was inserted by what's called short line. It looks pretty long to me, but it's a short line insertion into the tree canopy to get access to some of the remote wilderness grows. We do a lot of indoor grows as well. We have dealt with so many tanks, anhydrous ammonia tanks, and also ammonia generators. So we're cutting this out, scraping out the fertilizer, and sodium hydroxide, which starts a reaction which generates ammonia, which is condensed to form the Nazi cook method for methamphetamine. Or we have actual tanks that are supposed to hold anhydrous ammonia that are just super tough and not safe to handle with. So we take them out and remotely depressurize them, making them safe. And of course, the upcoming thing that we're all concerned about because of the toxicity and as well as impact to our society, right? This is killing a lot of people in the world. Fentanyl pill presses. We just had a fentanyl, work with WSP, a fentanyl pill press in a trailer. It's just ran into another one of these trailer mounted the other day. So that is ecology in a flash. Our spill response section. And then tomorrow, Sean's going to take it away and give you a little bit more detail about the event that led up to this lithium battery affair that we're having. Questions about ecology for Shanra? Yeah. Yeah, so let me see if I can summarize those questions for the folks who are listening online. There were two questions in there. At what threshold of lithium batteries should they reach out for help for disposal when it's going to be a disposal problem? And the second question was, how much water is too much? Creating maybe a public health or environmental hazard in the runoff. And I don't think I can confidently answer either one of those questions. That's part of why we're here, is to, pull samples from the residue, see what we're finding. I don't think there's enough data in the world right now to answer those two questions for you. I will, for your first question on disposal. Disposal is a tricky challenge, and the waste disposal laws are super, super complicated. So for us to bring waste, to take possession of waste and bring it back to the Department of Ecology, we don't actually have authority for that. That's creating, so under the federal and state waste management rules, so federal RCRA laws and the state dangerous waste regulations, which are fairly close, not identical. Washington State has taken RCRA, hazardous waste laws, added a few more extras on top of it, sprinkled with some extras, and called it dangerous waste, right? But there are tight restrictions about who can take the waste, who's the generator, the address of the property that the waste is, and where it gets picked up ultimately for disposal. And that whole set of regulations creates a real challenge for us, removing waste, taking it into our possession, hanging on to it until the disposal contractor comes and picks it up. Legally, that's tough for us to do. Even a waste agency like myself, that's tough for us to do. We have an emergency provision and direction from our state legislature, which is specific to drug labs, which requires us to go to drug labs, remove the chemical precursors, the contaminated equipment, and the waste generated in the production of illegal drug manufacturing facilities. And that gives us authority to bring it back and dispose of it as the generator. We don't have that for any other waste at Ecology. And my my facility staff is going to be really unhappy with me if I'm trying to find additional space in our waste lockers at the agency, because they're busting from the seams right now. We had a contract. I had a conversation with some other folks earlier today around the challenges in the waste disposal contractor community. They're having just systematic staffing shortages right now. It is tough for us to get waste contractors to show up and take our waste at our facility because of truck drivers, staffing, and even tracing it all the way back down the disposal chain to like the staff that run the incinerators. They can't run 3 shifts for the incinerators anymore, and they're having trouble finding staff for 1 shift. So that backs up the entire chain, and we are months behind. And so the waste thing is kind of a different challenge right now. It's what they can pay workers, it's supply chain, it's just all that feeding into a backlog of waste. Does anybody else experiencing that challenge that has waste to dispose of? All I'm seeing is smiles. Yeah. So what I'm hoping some of the testing that the CST is helping us do, and other testing that will happen as a result of this event, is so that we can maybe answer or at least formulate some tighter questions around what is the runoff, what concentrations are we looking at, what's the threat to public health and safety, what's the threat to human health and environmental receptors downstream from that? Because I don't have an answer to that. No, yeah. Those are hard balls. Somebody throw me some softballs here. Come on.
You work together with the EPA? Like we're talking now about lithium batteries.
Yeah.
The EPA classifies lithium batteries as disposal for recycling as universal waste.
Yeah.
However, we know they are not the same as the regular batteries that you use on the radio and so on. The results and the effects are different. How do you handle that?
Well, so Sean's going to cover that tomorrow. So we are pulling in contractor expertise to handle that. I mean, that is our disposal solution, and our solution, because we at Ecology can't legally take that waste, remove it, and then have a contractor come pick it up from us, because we become the generator and we're not. There's waste ID numbers and all sorts of other things that complicate that. and make our hazardous waste program at my agency very cranky if we do that. So we can't do that. We need to get them. We need to work with the example of Home Depot. They're the generator. We need the contractor to show up after the waste is stabilized at their facility and be picked up from their facility because they are the waste generator, and the generator ID for disposal is tied into the facility address. So and they're already generating waste, right? So they're a big business. They're generating waste not from arson fires, but just from their routine activities. So they'll likely already have a contractor available. They'll have an EPA waste ID number as a generator, and they should be set up for that. That for big businesses is pretty standard for the affair. So that's how Sean will fill in some details tomorrow, but that's how, except for the batteries that we borrowed from them for this event. Yeah, which they were more than happy to say, well, you want to burn these? Yeah, go ahead.
Yeah, those ones
Yeah.
wouldn't be an issue.
Yeah.
And that was referring to the Home Depot incident and so on. Because in that case, like they've all been exposed to fire, they're damaged now, and they are compromised. So whoever we move them from the location, we need to have some sort of special permit to
Yeah.
move them.
Yeah,
So,
and actually,
Yeah.
it's kind of timely having the discussion tomorrow because the contractor that was on scene is actually to be part of that discussion, which is actually also really useful.
Yeah.
Because we have the same questions. How are you profiling these? How are you getting rid of them? How are you managing this waste stream? Because for us, I mean, we treated the incident, specifically that Home Depot, it's like you would any other car wreck or anything else, right? There's been a fire, there's been damage. We can bring in an insurance agency or the insurance to be able to cover that and manage that work. And so that's where we wrapped our minds around it immediately. And like Dave was saying, the contractor that came is a contractor that they have on retainer. They use for all their other waste management and everything else. And they, luckily for us, had the capacity to be able to manage this incident because it was something that they were familiar with and they already had a plan in place to be able to do it. They were asking us all the same questions you're asking right now. What do we do with this? How do we pack it? Where do we go with it? Because it was something very new to them, even though they had a plan in place specifically for some of the other contracts that they had, which allowed us some of the materials that were needed. But ultimately, it fell back to that contractor. The one thing I would add on to too would be like the question about when to call. So like in the situation with the Home Depot fire, for us, we're a resource to this community as a whole. And whether or not we're packing it up, putting it on our trucks and taking it back or not, we're here to help. So like for the Home Depot fire or for that incident, even though we didn't load up, I mean, they had people on site for 4 days, back to back, 24 hours a day, packing that mess up. And like, even though we didn't pack it up and put it on our trucks, we were on scene with fire immediately to help them to work through that problem and to figure out what those flows were and what that proper process was and who to get it back to. And so we're always a resource to be able to help with that. I realize it's not as plain and simple as, hey, here's our problem, now it's your problem kind of thing. But at the same time, we're definitely there to help, and we're working towards those same answers. That's the questions and the skin in the game that we have here is, trying to figure out what that plan is. I mean, even the waste streams that we're generating today, right now with these burns, the whole focus of that is for us to be able to build profiles to figure out what those waste streams are going to be like for us to have to try and dispose of. And, by the grace of our upper management, the idea that they're willing to put forth that, just like everybody else is putting a piece into this puzzle, to try and figure out what the big overall solution or the big overall problem, or, how we're going to get there in the end together collectively. So I don't know if that helps or not. Any other questions? I know we said 4 o'clock and we're like 6 minutes late already. So.
If not, I was told to excuse you all. Have a great day.
See you guys
Yeah.
tomorrow.